Station Canada Theatre, located on the unceded territory of the Musqueam, Squamish, and the Tsleil-Waututh, for another edition of Ask an Astronomer, November 26th. Wow, this year has gone so fast. Our regular astronomer, Rachel, is away, so we are super lucky to have all the way across the country astrophysicist Nathalie Ouellette from the Université de Montréal. How are you doing, Nathalie?
Good. How are you?
Oh, not too bad. How are things over in Montreal?
Freezing rain.
Well, we have normal rain here in Vancouver, but I guess this is, we have a very diverse planet. We have a very diverse country. So we have a lot of different kinds of weather. And of course, you study lots of different kinds of planets, of course. Exoplanets is kind of your specialty, right?
So interesting, because I work at an institute where everyone is working on exoplanets. And so I learned a lot about exoplanets. I talk a lot about exoplanets. My research is on galaxies, actually. So I'm the black sheep in my family. I really work on galaxies, how they form, how they evolve. But in the last 2.5 years, I have learned lots on exoplanets.
Okay. Well, this is good because for the next half hour, we've got your brain that everyone on YouTube, if you want to ask questions about, we got a whole host of really cool stories to get through. But of course, if you want to ask Nathalie some questions about galaxies, you also gave a wonderful talk about black holes at our Cosmic Night earlier this year as well. So for everyone watching, if you have any questions, make sure to put them into the YouTube comments below and we'll answer them all until we get to our half hour mark. So let's go through some of our big stories, Nathalie. If you want to start sharing your screen, our first big story of the past couple of weeks is actually a bit of a sad story, but we can have a bit of a positive spin on it because we're talking about the Arecibo Observatory in Puerto Rico, which for as long as I can remember has been one of the most fascinating telescopes that I've ever learned about. And of course, it's popped up in so many different movies and it just looks super cool. So why don't you tell us about Arecibo, its legacy, and what happened to it?
Yeah, so Arecibo is a fantastic radio telescope. So it looks very different from what someone might imagine when they think of a telescope. You often think of a tube and there's a mirror in there or a series of lenses. But radio astronomy is very different. So something that most people don't know is that depending on the type of light that you're studying, your mirror or whatever kind of dish you're using to do astronomy can be more or less polished. So if you're looking at visible wavelengths or visible light, which we can see with the human eye, those are nanometers long, so a few hundreds of nanometers long. That's the wavelength of the light. And so your mirror can't have imperfections that are bigger than the wavelength of that light. But radio telescopes are interested in radio waves, which can be, centimeters or even meters wide in wavelengths. So you can instead do something that's a lot rougher, not polished like a telescope with a mirror in it, and use something like cement and concrete, those kinds of materials, and build these gigantic dishes. So Arecibo, 305 meters wide.
Wow.
Huge. It was the largest single dish telescope for centuries, for about 55 years until 2016, when the FAST telescope in China superseded it with a 500-meter wide dish. But still, 305 meters. It was built in a natural sinkhole, so they didn't build this hole. This hole was already there. Something that's pretty unique is that you can't steer it the way that you can for most telescopes. You can't just point it wherever you want because the dish is immobile inside of that sinkhole. But you can see suspended at the very center there a platform which has an antenna and a bunch of instruments, and that has a little bit of movement in it. So you can point it a little bit using that, but in general, you just have to wait until what you're really interested passes right above your heads. Yeah. So it's a very unique way to study space.
And I think I remember James Bond in GoldenEye climbing up onto the top there as he was escaping from the compound of whatever. I can't remember the details of the plot of that movie, but he was definitely filmed at Arecibo.
Yeah, that's right. And then you have 006 played by Sean Bean, who met his demise in that area. essentially.
Well, that's right. Sean Bean always dies. That's like
that's right. That's what I mean. I used to talk about Arecibo when I would give talks, and then I would tell people, and just so you know, spoiler alert, Sean Bean dies, but it's not really a spoiler alert because Sean Bean always dies. So.
Yeah. So this is really interesting because I know we have an observatory here at the Space Center, and we have a door, of course, that protects our telescope. We do get a lot of rain, of course. The telescopes that you work with obviously have to protect yourself from the elements, but this is wide open to the elements. So does rain, or perhaps I could even think of like perhaps some, bird droppings, does that affect this telescope, but because it's in the radio wavelength, it doesn't at all?
So you do have to have contingencies for when rainwater starts accumulating inside of the dish. There's ways for you to evacuate that. And birds will go and fly overhead and then, do what they have to do on top of it. There's a maintenance plan for Arecibo, but it has had a few very, very bad years. There was an earthquake in 2014 that damaged it. 2017 Hurricane Maria damaged it quite a bit. And the whole thing led up to the catastrophic breakage of some of its cables this year. So in August, a cable broke, and then November, a cable broke in a really catastrophic way. So you can see here, a 30-meter long gash was opened up inside of the dish, in the center of the dish. And so the National Science Foundation in the US, who is in charge of Arecibo, made an announcement, unfortunately, last year that it was no longer able to fund it, and to try to repair it would actually be dangerous for its workers. So it will be decommissioned, and they're building a plan now to decommission it safely.
Oh, that's just super sad. Do you know, so this is the biggest radio telescope in the world. Are there, what other kind of second biggest? So, tell us about like, what are we looking for when we're talking about radio astronomy? Because, many people think of, using optical telescopes that we can see planets, that we can see galaxies. What are we really looking for with a radio telescope?
So a radio telescope, and people who work in radio astronomy, I have to say, they're their very own breed of astronomers. They're very different from the other astronomers in my mind, because even if I work with things like spectroscopy, which aren't quite as usual as just a nice image of a galaxy or a planet or something, it's still light in a way that my brain can understand it. But people who work in radio astronomy, they find like the power spectrum of objects, and they have to put mathematical equations called Fourier transforms on those to try to convert the signal that they get into an image. So the parallel that I try to draw is, in the Matrix, when at some point you have some of the characters that are looking at screens, that there's just all of these like green numbers passing over the screen. Mm-hmm. And then they say, oh, I don't even see the code anymore. I just see, like this person walking around in the Matrix. Radio astronomers become that. Like, they see all of these weird signals and mathematical things, and they see a galaxy in that. So it's very, very different. They have to do some weird stuff to their data that I am not accustomed to. So that's the first disclaimer that I can say about radio astronomy, but it's super interesting. Yeah. Arecibo and radio telescopes around the world study super interesting things. And some of the things they do is try to find aliens. So there was a message in 1974 called the Arecibo message that was sent out, and you can see a sort of pictogram that depicts it here. It was in binary code. It was sent out towards a globular cluster, so a bunch of stars held together by gravity about 25,000 light years away. And it sent a message of, who we are, some of the animals that live here, a little bit of music that we have, a little bit similar to the golden disc that was sent on the Voyager spacecrafts. So we haven't received a reply yet, but technically we only sent it about 45 years ago. So it hasn't really arrived to its destination yet. So who knows, if we'll receive a reply. So finding aliens is something we do with radio telescopes. But some other things that we try to do, we study some very exotic phenomena, including pulsars. So the Crab Nebula was the collapse of a massive star that happened around the year 1000. And astronomers saw the supernova go off in our sky. It was brighter than, you could see it during the day, actually, was so bright. And at the very center, you have a dead star that is doing some really weird things. It's called a pulsar, and it pulses light very, very brightly, several thousands of times every second, like a really hyperactive lighthouse. So
Wow.
they emit brightly in the radio telescope. And one last thing that I could mention is Arecibo was super important in detecting and tracking all kinds of asteroids that are flying near the Earth. So it was really essential in trying to track these and making sure that they don't smash into the Earth. So yeah, that was an important legacy of Arecibo.
You know, I can imagine, if the Arecibo message ever makes it to a destination and then they figure out, okay, we'll have to reply in the same type of information. It looks like they're going to have to find someone that remembers how to play Atari, because that's what the Arecibo message kind of reminds me of.
Yeah, it looks very old school.
So our first question actually coming in, so just to follow up on what you're talking about with, we're sending out the Arecibo message, but we're also sending out lots of other signals as well. And we have been, since the 1930s, I guess. How far into the universe have we been sending messages?
So if we've been sending radio messages for maybe 100 years or so. So technically those radio messages, they go at the speed of light. So they have potentially reached as far as 100 light years away from the Earth. To sort of place how far that is, how big of a bubble that is, the closest star to the sun, Proxima Centauri, which has an exoplanet on it, a rocky exoplanet that is, potentially inhabited, but we have no proof of that. That's about 4 light years away.
Yeah. Okay.
So those people have been getting, if there is anyone on that planet, they've been getting our stuff for a long time. They can see, like they saw GoldenEye, the James Bond movie, passed by technically, but those messages are not targeted to an extraterrestrial source. So they're not necessarily very strong once they reach out there. It wasn't like the Arecibo message where we're really sending a clear message in that direction. So even though technically those radio waves could reach 100 light years away, they might just be garbled mess at that point.
Yeah. So because they're 4 light years away, they're kind of 4 years behind us, which means they just realized that there's a new president in the United States. So they're probably like, oh, what's going on down there?
Exactly.
Awesome. So really amazing telescope. Really sad that it's gone, but we will rebuild more. And of course, radio astronomy is not completely dead, just an old friend that we're saying goodbye for now.
Mm-hmm. That's right.
Let's move on to our next big story. Somebody is actually calling me. Can you believe it's coming?
Oh, you have some call-in questions?
Call-in questions. Should I loop them in? Oh, it's spam. I should have answered it. Let's move on to our next big story. You did talk about asteroids. We did talk about an exoplanet. So our next big story was this discovery of a rogue planet. And first off, Nathalie, tell us, what is a rogue planet?
So it's a pretty cool name. I love rogue planet. So all planets are born inside of systems where they are orbiting stars, but the early life of a solar system or any kind of stellar system can be very, very turbulent. And during that time, some of the planets that were formed in the system can be kicked out of the system. And we think that it's very likely that the solar system had more planets than it has now at its very beginning. And while everything was sort of forming and placing itself, we probably kicked out some planets as well. So those planets that are ejected from their systems become just free floating. They just blast off into space, unattached to any star. And that's what we call a rogue planet. Interesting.
So how exactly can we find rogue planets? I mean, as we've heard in previous talks, just finding exoplanets is difficult enough because planets don't give off light. They have to be close to a star. So we can imagine that a rogue planet, if it doesn't go around a star, how can we possibly find it?
Yeah, they're actually really hard to spot because usually, as you said, we're not detecting the planets themselves. We're detecting the effect of the planet on their star. Sometimes you can image a planet. Very, very young planets do emit brightly, especially the really, really big ones, some that are 5 or 10 times the mass of Jupiter, they have their own inner heat, especially bright in the infrared, so you can image them. But typically, even when you consider the ones that are orbiting planets, we only know a few dozens of those that we've been able to take a real image of. So for work planets, usually it takes a very particular set of circumstances, such as them passing in front of a star, and their gravitational effect will cause a small micro lensing of that star. And it's not that they're attached to the star. It just so happens that they're passing between us and that star. So we still need to observe these rogue planets based on an effect that they have on their environment. It's very hard to spot them all alone because they're not very bright.
Right. So I can imagine, like, do we know much about this this new rogue planet that was recently published by a team?
We can tell how massive it is, because the more massive a rogue planet is, or any planet is, the stronger the gravitational lensing effect it will have. So essentially what happens, gravitational lensing is the warping of space due to some mass, and the light shining throughout that space will also be deformed or warped. So that happens a lot when you have galaxies, really big galaxies, and you'll have like these Einstein rings that happen. These faraway galaxies will be deformed into these rings or these arcs or anything like that. But you can have microlensing effects where a planet will pass in front of the star, and for that small moment in time, the light of that star will be focused, hyper-focused towards us, and the star will look a little bit brighter than usual. So it'll increase in brightness. But the more massive that rogue planet is, the higher that peak in brightness is. So we can actually tell a little bit about how big these rogue planets are, how massive they are, based on how much they affect the light of the star.
Wow, amazing. Just incredible. Our universe just keeps giving us so many surprises. It gives
us these clues, but they're very hard to decipher. So you have to work pretty hard.
But this is right out of science fiction, right? You know, like a planet just like freely floating through the universe. Yeah, can you imagine like if there could possibly be any life on this thing? I mean,
it would be rough because it would totally change the conditions on that world. You know, you wouldn't have constant light or heat or anything like that there. So in all likelihood, if like the Earth were to go rogue suddenly, we wouldn't be able to survive that. We need the sun.
Yeah,
so it's probably the same thing for other life on those planets as well.
Amazing. So if you have any questions about rogue planets, put them into the chat. We're still finding more. This is a relatively new topic, but the next big story that we're going to cover for this week was the discovery of another bit of a mystery of the universe, and that's fast radio bursts, often called FRBs, which does get back to radio telescopes and, of course, messages from beyond. And when fast radio bursts were first discovered, we didn't quite know what exactly they were, right, Nathalie?
No, and we're still not quite sure, but we're a little bit closer now because we have at least one working theory, and we have some amount of proof behind that theory. But before, it was basically anyone's guess. And anytime you have a radio signal, especially one that repeats at a constant frequency, people will think aliens immediately. But, you know, we have to have proof that it's aliens before we can say that. We don't yet have proof that it's aliens.
Yeah.
Yeah.
So absolutely. So these fast radio bursts are coming from somewhere in the universe. So what have we discovered recently?
So recently, thanks to the Chime telescope, which is actually in Picticton in BC. It's a Canadian telescope with leadership at UBC and also at McGill University in Montreal, where I am. And they are looking specifically for fast radio bursts. And they've been finding lots of them in the last few years. But a few weeks ago, they found one that was much closer to home than usual. Usually these things are in distant galaxies, very, very far away, such that we can see the fast radio burst, but we can't associate it with any one phenomenon. It's just something bright that happened in that faraway galaxy. We have no resolution to tell what's going on. But the one that we detected a few weeks ago is only 30,000 light years away from Earth, but it's inside the Milky Way, which makes a big difference. And it was actually confirmed that the object that was creating that fast radio burst is a magnetar, which is a form of pulsar, which I mentioned before. It's those dead stars that happens at the end of a very massive star's life. And it's flashing light brightly. But magnetars, on top of having all of those interesting characteristics of a pulsar, have really, really intense magnetic fields. Its magnetic field is about 1,000 trillion, or like 1 quadrillion times stronger than the magnetic field of the Earth.
Wow.
So really, really strong. So it appears that at least one theory behind the source of these fast radio bursts would be magnetars. But it could be that many different things create fast radio bursts, not only magnetars.
Okay, so definitely not aliens then, are you sure?
At least for this one. Or they're being sneaky and they're hiding behind a magnetar.
I guess, you know, if we wanted to mask it, I guess at least we'd know what we'd try to mask it with. You know, we'd try to make it mimic a magnetar, right?
Yeah, that's right.
So we do have some more news stories to get to, but let's get to some questions and we'll just open it up and see what we got, because we got about 10 more minutes till we have to let Nathalie go. So let's go back to rogue planets. And CL Chen asks, can rogue planets attach themselves to a new solar system?
So that's a really good question. And theoretically, it could. But because stars are so far away from each other, the chances of that happening are very, very, very slim. People don't realize how empty space is. So one of the ways that I try to make people imagine that is, as you might know, our galaxy, the Milky Way, which is filled with like 200 billion stars, is going to crash into the Andromeda galaxy eventually, which might have as many as 1 trillion stars. And those stars, a lot of those stars have planets around them and everything. When that happens in the collision, the chance of any one star in the Milky Way colliding with any one star in the Andromeda galaxy is 1 out of a million. So, and not like for any one star to collide with like some, like, in all likelihood, nothing will directly collide with anything because space is just really, really empty. So you would just have to have the rogue planet pass right next to a star for it to attach. It could theoretically, but it's just so unlikely to happen because space is so empty.
And haven't we had sort of examples of that recently with Oumuamua, that very strange object that flew into our solar system that was not part of our solar system and then just kind of like came and went very quickly?
Yeah, so that was an asteroid. In all likelihood, some kind of asteroid, comet. The verdict is still out. Unfortunately, we only detected it when it was already on its way out, so we had very limited time in order to study it. But that was probably part of some planetary system, and it got ejected out of its system, and it happened to pass by close enough to enter our system. But because of its dynamics and because it was actually moving so fast, it only passed through. It didn't actually get caught up in the gravitational pull of the sun. So these rogue planets can have their trajectories changed and diverted. But for it to attach itself, not only would it have to pass close to a star, but it would have to pass by slowly enough for it to attach itself. Otherwise, it's just going to like sort of cruise on by.
Yeah, interesting. Let's keep on going with some questions from our YouTube audience. Back to Mai. Fast radio bursts travel at the speed of light? Question mark?
Yeah, so radio signals are just a form of light. All forms of light are included in what we call the electromagnetic spectrum. And the part of that spectrum that we are most familiar with is visible light. It's what we tend to call light every day. It's what we can see with the human eye. But infrared light, ultraviolet light, X-rays, gamma rays, microwaves, and radio waves are also all part of that spectrum. They're all forms of light. So they are, it's photons that are traveling across space that transmits those waves. And so they're all traveling at the speed of light.
Yeah, and it's good to remember, because I remember me getting tripped up when I was young is trying to separate the speed of sound and radio, because speed of sound and radio aren't the same.
Yeah, but we tend to associate radio waves because we listen to the radio, but it's not quite the same thing. What that information that's being transmitted by those radio waves happens to be sound, but it could be something else. So the information is going at the speed of light, and when we receive it, we're hearing sound.
And as you already showed, we can turn radio waves into really cool Atari images.
Yeah, that's right.
Let's keep going with some questions here. We're going to open it up to some random ones. We're going to go to Jennifer Mendoza, who says, "Hi, Nathalie. What is the difference between dark matter and dark energy? What consistency would you say they are? Gas, plasma?"
So
just the small questions for you.
Yeah, tiny question, easy to answer. So dark energy and dark matter are very different, but they're both called dark because we have close to no idea what either of them are. But dark matter, we're in a better state. So dark matter is, in all likelihood, some form of matter that is very unlike the stuff that is all around us. It's normal matter or baryonic matter that interacts with everything around us through the four forces of physics that we know. So gravitational force, the electromagnetic force, the weak and the strong nuclear forces. That's normal stuff. Dark matter doesn't seem to emit, absorb, or reflect light. So it doesn't interact through the electromagnetic force. That's the force that governs light. But it does have a gravitational effect. And we see lots and lots of this dark matter in space. There's about 10 times more dark matter than there is normal matter, but we don't know exactly what it is. But at least we sort of know that it's some kind of matter. It might be a type of particle we've yet to discover, and we're working on it. We have people who have built detectors to try to detect dark matter. So that's part of the equation. Dark energy is even more mysterious. It's a form of energy that appears to be causing the universe's expansion, not only the expansion itself, but also the expansion to accelerate. So the universe is expanding, and for a long time, we thought that it was going to slow down, eventually stop, and maybe recollapse on itself to form a big crunch and eventually another big bang. But in the 80s and 90s, we were able to calculate how fast it was expanding, and we realized it was actually expanding faster and faster, which is a little bit alarming. That was the opposite of what we were expecting. So we invented this concept of a dark energy that permeates all of the universe, and it appears to grow more and more in strength and force as the universe gets bigger. So it doesn't act like normal energy or matter, and it almost serves like a kind of pressure or an anti-gravity that pushes on the boundary of the universe. So they're both important in our understanding of the universe. They're both very mysterious, but dark matter, I understand more than dark energy.
You and me both. But if you want to go and learn more about dark matter, we actually had a whole cosmic night, which is on our YouTube channel. Just search for that. We had a wonderful talk by Dr. Tian Yu from the University of Oregon. She dived right into dark matter. Go and check that out. All right, let's go to Megan Rose, who is looking for a bit of advice. Nathalie, what university courses do you recommend to eventually work on analysis processing of astronomical data, especially planetary data?
That's a great question. It depends on what program you're in. So now it's part and parcel of any sort of physics program to do programming classes. We are basically just human computers who are using computers to try to analyze astronomical data. So anything that teaches you scientific programming, Python is an especially versatile language that you can use. So that's very, very useful. Statistics is also very interesting because now we're going into the realm where we have so much data that to understand how all of this different data, what it means, we need to know statistical methods in order to make sense of all of it. So statistics is also very important. And also, if you're just wondering if you want to go into astronomy, most departments or most universities will have a sort of Astro 101 that doesn't necessarily have the math to start off with, but it goes through astronomy from a qualitative basis. And then you can sort of figure out if you're interested. And if you are, you can start looking into the curricula of your physics department, where you really get into the nitty-gritty of the stuff.
Wow. Yeah. It's super amazing. And sort of, was that, what was the path that you took in school? Like, what did you first take when you started?
It was a pretty typical traditional path. At McGill University, where I got my bachelor's degree, there is no astronomy department. Those are very rare in Canada. The only place that we have that, a separate astronomy department from the physics department, is at the University of Toronto. But I was very happy I'm happy to have a physics bachelor's degree because I feel like I have a very solid background. I had to do quantum physics and electromagnetism and general relativity and all that kind of stuff. And then afterwards, well, while I was doing my physics bachelor's degree, I was doing astronomy research during the summer for internships. And that's when I really knew that research was something I wanted to do. And then I went on to do a master's and a PhD at Queen's University in a physics department, but in the astronomy research group.
Oh, amazing. We basically right up at our time right there. But one last question from CL Chen. So you talked about sort of the expansion of space. So do we actually have like a calculation of how much space that we've discovered to get can we actually measure that?
So there are two different metrics that you can use when you're talking about the size of space. There's the size of the observable universe and the size of the real universe. So something really tricky happened very early on in the history of the universe called inflation. And for a small moment in time, the universe actually expanded faster than the speed of light. That doesn't actually break the laws of physics. The laws of physics says that anything in the universe can't go faster than the speed of light, but it doesn't say anything about the universe itself not being able to go faster than the speed of light. So it still works out. But because that happened, that means that at some point in time, the universe blew up so big that in order for the light of whatever's going on in that area to reach us, we would need more time than the universe has been alive for us to see what's beyond there. So we are able to see a certain amount of observable space, but we know there's something even beyond that that is completely unknown and inaccessible to us. So it's difficult for us to figure out. And we can only try to estimate the size of that using fundamental physics equations from theory on what we think happened during the Big Bang.
Amazing. Well, Nathalie, thank you so much for joining us for another edition of Ask an Astronomer. If people want to learn more about what you're up to over there on the other side of the country, where can they go?
They can go on my institute's website at exoplanets.ca, or they can go on my personal website, astropanda.space, or they can follow me on Twitter at angryastropanda.
Wonderful. Well, thank you so much. You were a friend of the MacMillan Space Centre. We hope to have you on and join us for another program soon.
Thanks for having me.
Awesome. Thanks to everyone for joining us. We will see you again in 2 weeks.